The Web3 revolution was supposed to give us freedom, a digital world owned by its users, not controlled by corporations. But that dream came with a hidden cost: security. Every week, another decentralized project falls to hackers, and trust in blockchain technology takes another hit. What if there was a way to change that? What if one blockchain wasn't just promising decentralization, but had actually built the tools to make it secure, from the code to the cloud? Today we're exploring how the Internet Computer, or ICP, is redefining what Web3 security really means. From Canister smart contracts to chain key cryptography and a self-governing network that heals itself, this isn't just another blockchain story. This is how ICP is quietly building the most secure foundation for the next era of the Internet. This video is created for educational and informational purposes only. It does not promote or endorse any financial product, investment, or cryptocurrency. All information presented here is based on publicly available sources and independent analysis. Viewers are encouraged to conduct their own research before making any financial or technological decisions. The decentralized web promises a new era of freedom, but it comes with a major problem: security vulnerabilities. Every week, it seems like another Web3 project is compromised. Billions are lost to exploits, bridges are hacked, and protocols collapse under their own complexity. But what if one blockchain has cracked the code on true decentralized security? Imagine a Web3 where your assets are truly safe, where smart contracts are virtually unhackable, and where decentralized applications run with unprecedented integrity. This isn't a distant dream. It's the reality ICP is building. Today we'll explore how the Internet Computer, ICP, has taken a revolutionary approach to securing the decentralized web and why it might just be the blueprint for Web3's future. Before diving into ICP's innovations, it's important to understand the scale of the problem. Web3 was built on the promise of decentralization, removing intermediaries and giving users true control. But that promise came with trade-offs. In traditional systems, centralized entities provide oversight, audits, and accountability. In Web3, the same freedom that empowers users also creates opportunities for vulnerabilities. Over the past few years, we've seen some of the biggest names in crypto fall victim to security breaches. Smart contract bugs, faulty bridge protocols, and weak consensus mechanisms have cost the industry billions. The truth is, many blockchains were designed with scalability or speed as their priority, not security. As a result, Web3 remains fragile, a frontier full of potential but riddled with risks. This is where ICP stands apart. Instead of patching existing weaknesses or depending on external validators and third-party security tools, the Internet Computer reimagined blockchain architecture from the ground up. Security, for ICP, isn't an add-on, it's the foundation. ICP, developed by the Definity Foundation, is one of the most advanced blockchain networks in the world, not just in terms of performance, but also in its approach to protection. It doesn't rely on the same model that powers most other chains. Ethereum, Solana, and others depend on smart contracts that interact with external oracles, centralized front ends, and traditional cloud services. Each of these layers introduces potential attack vectors. ICP eliminates many of those vulnerabilities by doing something radical. It brings the entire stack, computation, storage, and web hosting, on-chain. Applications on ICP don't just run on a blockchain, they live entirely within it. That means everything from logic to data to front-end interfaces is secured by the blockchain's cryptographic backbone. This holistic design is a major shift from traditional models. It creates a self-contained, tamper-proof environment for decentralized applications, known as Canister smart contracts. These canisters represent a significant evolution of the standard smart contract, designed with built-in security, scalability, and interoperability in mind. Traditional smart contracts are powerful but fragile. They're often limited by gas fees, external dependencies, and human error in deployment. ICP's Canister smart contracts change the game. A canister is not just a contract. It's a full-fledged computational unit capable of running complex logic, storing data, and even serving web content. Every canister is secured by the Internet Computer Protocol itself, which ensures deterministic execution and verifiable state changes. This means that every action within a canister is cryptographically secured and replicated across nodes, making unauthorized manipulation virtually impossible. Canisters also benefit from deterministic finality, a critical factor in maintaining security consistency. Unlike probabilistic finality models, where transaction confirmation can still be reversed under certain conditions, ICP's deterministic finality guarantees that once a transaction is confirmed, it's permanent. This eliminates rollback risks and double spend attacks, ensuring absolute integrity in every operation. Another unique advantage is the reverse gas model. On most blockchains, users pay gas fees to interact with smart contracts. This introduces complexity and, in some cases, vulnerabilities related to front-running or transaction delays. ICP reverses that model. Developers, not users, cover the computation cost. This makes dApps smoother, safer, and more accessible to mainstream users while eliminating one of the major friction points in Web3 usability. While the technical design of canisters provides structural security, ICP goes further by embedding governance into its security model. The network nervous system, NNS, serves as the brain of the internet computer. It's a decentralized, autonomous governance system that manages network upgrades, node additions, and protocol-level decisions. The NNS operates through neuron voting. Participants stake ICP tokens, lock them into neurons, and vote on proposals that shape the network's evolution. This governance structure ensures transparency and decentralization, but it also acts as a form of security oversight. Instead of depending on centralized teams or foundation-led updates, the community collectively governs the network's core decisions. One of the NNS's most powerful attributes is its ability to implement autonomous recovery. If a vulnerability is detected or a component fails, the NNS can propose and execute network changes automatically. This self-healing capability is unprecedented in blockchain, turning security from a reactive process into a proactive, adaptive mechanism. At the heart of ICP's architecture lies chain key cryptography, CKC, one of its most groundbreaking innovations. This technology allows ICP to sign data and verify transactions using a single public key, regardless of how many nodes or subnet blockchains exist behind the scenes. The result is a seamless, secure, and scalable network where users can interact without relying on complex or redundant cryptographic layers. Chain key cryptography enables ICP to achieve true decentralization with unmatched efficiency. It supports instant verification and enables direct communication between subnets. More importantly, CKC allows ICP to interact securely with external blockchains and Web2 systems, paving the way for cross-chain security solutions. This system is also crucial for end-user trust. By maintaining a single verifiable public key, ICP removes the need for intermediaries or third-party verification. When users interact with an ICP-based dApp, they can trust that every piece of data, transaction, and interaction is authenticated by the protocol itself. Security in Web3 doesn't stop at smart contracts or cryptography. It extends to infrastructure. Many blockchains rely heavily on centralized cloud providers like AWS or Google Cloud to host front-ends, APIs, or node operations. These dependencies create hidden vulnerabilities, as central points of failure can be exploited or censored. ICP breaks away from that model entirely. It runs on independent data centers operated by node providers across the world. These nodes are coordinated through subnets that together form the global internet computer. Each subnet has its own consensus mechanism, but remains connected through chain key cryptography, allowing seamless global operation without centralized control. This decentralized infrastructure ensures redundancy, resilience, and resistance to censorship. Even if several nodes go offline, the network remains operational and secure, something that's rarely achievable with traditional blockchains or Web2 systems. ICP's security model extends beyond architecture. Its reverse gas model ensures transaction integrity by removing the dependence on volatile gas markets. Its deterministic finality guarantees that transactions are final and irreversible. Together, these systems build a level of reliability that's critical for enterprise-grade adoption. The platform also includes native identity management tools such as Internet Identity DY, a privacy-preserving authentication system that allows users to log into dApps using biometric or hardware-based keys instead of passwords. Internet identity is designed to prevent phishing, identity theft, and data leaks while maintaining a seamless user experience. When combined, these features create an ecosystem where every layer, from computation to governance, contributes to security. Instead of bolting on defenses after launch, ICP integrates security at the protocol level. It's not an afterthought. It's the core principle. Real-world impact, secure dApps, and use cases. ICP's security. First approach isn't just theoretical, it's proving itself in real-world applications. Dozens of dApps are already leveraging ICP's architecture to build secure, scalable, and user-friendly Web3 solutions. Projects like OpenChat, a decentralized alternative to messaging platforms, demonstrate how user communications can be end-to-end encrypted and hosted entirely on-chain. Similarly, DSCVR and District showcase social media applications that are immune to data breaches and centralized censorship. In the DeFi space, ICP's predictable computation and deterministic finality make it ideal for financial protocols that demand stability and security. The combination of scalable infrastructure and tamper-proof canisters allows developers to build products that operate with near-zero downtime and zero trust requirements. Even beyond crypto-native use cases, ICP's architecture opens doors for enterprise and government applications. Its ability to host secure web services on-chain means organizations can deploy systems that meet both performance and compliance needs without relying on centralized servers or intermediaries. Enterprise potential and critical infrastructure. The implications of ICP's model extend far beyond decentralized apps. Its security protocols are robust enough for mission-critical infrastructure. Governments, banks, and corporations can theoretically deploy full-scale systems directly on the Internet computer, from secure data management to digital identity frameworks. Because of its verifiable execution environment and deterministic guarantees, ICP provides a transparent and auditable framework for industries that handle sensitive data. The potential here is enormous. Imagine national ID systems, financial ledgers, and communication networks that operate entirely on a tamper-proof blockchain layer. This is where ICP moves beyond being just another blockchain. It becomes a universal computation layer for the Internet itself. By integrating Web3 security principles into the very fabric of online infrastructure, it's redefining what secure digital trust can look like. As Web3 continues to evolve, security will remain the defining factor separating successful ecosystems from those that fade away. With the growing complexity of decentralized networks, relying on patches and audits isn't sustainable. What the Internet computer offers is a fundamental rethinking of how security should work, embedded into every line of code, every node, and every interaction. ICP's multi-layered approach, from chain key cryptography to canister-based computation and autonomous governance, sets a new benchmark. It proves that scalability, speed, and decentralization don't have to come at the cost of safety. In a world where hacks and exploits dominate headlines, ICP presents a model that could make them a thing of the past. To sum it up, ICP's unique value proposition lies in its integrated end-to-end security design. It's not just a blockchain, it's a secure operating system for the decentralized Internet. Its canisters redefine smart contracts, its NNS governance introduces adaptive resilience, and its cryptography ensures data integrity at scale. For developers, this means a platform where innovation doesn't compromise safety. For investors, it represents a network with long-term sustainability. And for users, it promises a digital world where ownership and trust are finally protected by design. The decentralized web is only as strong as its foundation, and ICP's foundation is built on security. As the industry continues to mature, the Internet computer stands out as one of the few networks capable of supporting Web3's vision without sacrificing integrity. The future of decentralized security isn't just about preventing hacks. It's about building systems that can't be compromised in the first place. And in that future, ICP is already leading the charge. All right, if you learned something new or enjoyed this video, make sure to hit that like button, subscribe to the channel, and turn on the bell icon so you don't miss future updates. Thanks for watching, and I'll see you in the next one.